Welcome. My name is Elliot.
And I'm Turkey.
I'm Tesfa.
Welcome to Phase Transformations for Steel. So what is phase transformation? Phase transformation is the alteration of microstructures of a material to gain different properties.
Why does it occur? It basically occurs through a combination of heat treatment and quench time, which is basically just extreme temperatures and how long you would actually quench the heat within water to see what phase it would actually land in. Why do we do it? We basically do it just to get different kinds of steels because there are different kinds of steels that have different hardness, softness, ductility, and to see whether it's brittle or not.
And where do you see it? You see in industries such as knife making. You want to affect your knife properties to have a stronger, harder material. And you also do it in component making such as gears. In construction, you may want a gear that can handle more stress or take more impact
And toughness.
and have a tough material.
Hawkers. Two examples of hawkers are material scientists and component designers.
So this is a phase transformation diagram. Our axes include on the x-axis, you have time. It's a log scale in seconds. And then on the y-axis, you typically have temperature in degrees Celsius, and you'll have Fahrenheit on this side. Now, a phase transformation diagram is specific to a material of one composition. So in our case, we're doing steel. It's specific to the composition of both iron and carbon.
So we have here the austenite, and this part is perlite, benite, and everything below is martensite.
So basically, to get to these areas, you would start with your austenite here above the anthropoid line. And once you would quench the temperature, you would go to either phase to basically get a different kind of steel. Because every phase has a different kind of steel. Basically. Alright, to start off a phase diagram, what you would need to start off with is austenite. Austenite is basically just a metallic non-magnetic solid solution of carbon and iron, which is basically just pure iron. It's only ever stable around a temperature of 910 degrees Celsius. Apart from that, anything lower than that, austenite is actually pretty unstable. As it cools, the structure either breaks down into a mixture of ferrite and cementite, which is usually in the structural form of perlite or bainite, or it undergoes a slight latex distortion known as martensite. It is very soft and ductile, but can dissolve considerably more carbon. Perlite. Perlite is what's formed between when you cool austenite between temperatures 727 degrees Celsius and 540. The more coarse the perlite, the more layers will be able to stretch out, and the more ductile it could be, as you can see in the picture to your left. The finer the layers making up the perlite, the more they're going to resist slipping relative to each other, and the stronger the steel is going to be, as you can see in your picture to the right. To form coarse perlite, you have to stick it in another furnace once you've already heated it up. One that is kept between temperatures 600 and 700 degrees Celsius. To make fine perlite, simply putting it out on the furnace and letting the air just cool it pretty much will be significant enough to lower it to room temperature, thus making fine perlite. It's not very strong or hard, but it is actually quite ductile.
Benite is a non-equilibrium phase morphology of steel that can occur at temperatures of 250 to 550 Celsius, placing it as a state between perlite and martensite. The plate-like structure of benite is almost identical to that of martensite. It consists composed of cementite and dislocation-rich ferrite. Despite the similarities to martensite, differences can be observed by using transmission electron microscopy. Benite is less reflective and thus appears darker under this process. Benite forms a nearly parallel layer, often separated by plates of ferrite. There are two levels of benite. Upper benite forms at 400 to 550 degree, and lower benite forms between 250 and 400 degrees Celsius. Benite was completely unknown until the 1920s, when E.S. Davenport and Edgar Bain discovered it while working at the United States Steel Corporation, and Bain's colleague began referring to the microstructure as benite in his honor. Spheroidite is a phase of steel structure made up of spheroids of cementite surrounded by either ferrite or perlite. Depending on how the spheroidite is achieved, primarily spheroidite is achieved by heating the steel to 700 degrees Celsius for over 30 hours, but it can also be achieved at lower temperatures over longer periods of time. Spheroidite is noteworthy as a phase of steel transformations because it has the softest and most ductile form of steel. This allows the steel to be easily shaped and even made into long wires without even breaking.
Martensite is austenized iron-carbon alloy that is rapidly cooled or quenched to a relatively low temperature. This non-equilibrium phase occurs when the quench rate is rapid enough to prevent carbon diffusion. Now, diffusion is what results in ferrite or cementite phases within the crystal structure. Now, the austenite starts as an FCC crystal structure that experiences a polymorphic transformation to the BCT martensite crystal structure. Now, the martensite crystal structure can exist almost infinitely at room temperature. Martensite transformation does not involve diffusion. Martensite grains nucleate and grow at the speed of sound, so the process almost occurs instantaneously. When they occur at this rate, it actually becomes independent of time, so the process itself is solely dependent on the temperature at which the material is cooled. Now let's look at a demonstration on how martensite is formed. It begins by heating steel to 727 degrees Celsius. This forms the austenite phase. Then it is rapidly quenched to a relatively low temperature. Now this causes the martensite to form. Now let's look at the crystal structure while this occurs. Looking at it at 10 micrometers, we can see the austenite and then the nucleation and growth of a needle-like structure within it. This is the formation of martensite. Now all of the white you see in the background, this is unchanged austenite. Martensite can coexist with other phases such as perlite. Now some properties of martensite is that it is harder and stronger than all other phases, but it's also more brittle. Now the hardness is actually dependent on the amount of carbon in the steel, up to about 0.06% carbon. Now if you're quenching large pieces with a composition greater than 0.5 weight percent carbon, this can result in cracks as a result of the volume increase during the phase change. Now this volume increase occurs because austenite is denser than martensite. Quenched martensite may have internal stresses that weaken the structure. These stresses can be removed with tempering. Tempering is done by heating martensite to a temperature below the eutectoid point for a period of time. This temperature falls between 650 to 250 degrees Celsius. The heat treatment at these temperatures allows the diffusion process to occur, forming tempered martensite. Now martensite starts as a BCT crystal structure and transitions to tempered martensite, which is an alpha plus iron 3 carbon phase. Now, it is composed of stable ferrite and semonite phases. Now, it consists of extremely small and uniformly dispersed semonite particles embedded in a continuous ferrite matrix. Now, this structure will look very, very similar to a spheroidite structure, except the semonite particles are much, much smaller. Now, tempered martensite is nearly as hard and strong as martensite, but it has much better ductility and toughness. The hard semonite phase reinforces ferrite along boundaries, which act like barriers to dislocation motion during plastic deformation. And then the ferrite provides ductility and toughness for the structure. Now let's take a look at the formation of tempered martensite. You initially start with martensite and then heat it up below its eutectic point, typically between 250 and 650 degrees Celsius. And then you slow cool the metal back to a lower temperature. Now let's take a look at what's happening at the microstructure. At 1 micrometer, once it's slow cool after being heated, you can see the formation of semonite in between the martensite crystal structure. Now this is converting remaining austenite to semonite. And here's a quick physical demonstration of how martensite is formed. We have a piece of steel that we're heating with a 2000 degree torch. This puts it into the austenite phase, and then it is rapidly cooled or quenched. That transforms it into martensite.